Okay, problem number 37. You have a polynomial over a polynomial. You check the degrees. You've got degree 2 over degree 4, so we do not need to do any division. In the denominator, you have a parentheses squared. In that parentheses, you have a quadratic. If you can factor that quadratic, you want to. If you look at b squared minus 4ac, the formula under the square root of quadratic formula, that's going to be 16 minus 4 times 1 times 6. A negative number. Negative under a square root says no real solutions, which says factoring not going to happen. Ha, ha, ha. So we are stuck with dealing with a quadratic. And the reason why we weren't wanting that, you will find out with this problem, why we want to avoid quadratics if we can factor it down to linears. So with a repeated quadratic factor, that means that this integrand can be fraction decomposed, into parentheses squared plus same thing to the 1 power. So when you have a repeated factor, you put its highest exponent or that exponent on there, go down by 1, and keep going down by 1 until you reach 1. So yeah, that was as far as we went. Put that quadratic in, and if it is quadratic at the core, then you're going to put linear above it, some ax plus b, and cx plus d. And now that equation, we are going to multiply both sides by this denominator. The left side is now the numerator x squared minus 3x plus 7. On the right, ax plus b plus, and then I've got to make sure to multiply cx plus d with one more x squared minus 4x plus 6. And I want to expand, so I'm going to distribute cx over the second parentheses, cx cubed minus 4cx squared plus 6cx. Then I will distribute the d over the second factor plus dx squared minus 4dx plus 6d. One thing that I see right away is I've got an x cubed term on the right side, just one, solitary. On the left side, I don't have an x cubed term. It's quadratic. That means c must equal 0. Does everyone see that? If I don't have that term on the left side, then the coefficient is 0. Now, with knowing that c is 0, I'm going to pop that in so that I have less to try to work with. That means I've got ax plus b, that's gone. And oh, look at that. Bye-bye. And bye-bye. Ooh, that just really brought things down. And now I can see that I only have a single term with x squared in it once I make that realization. And the coefficient on the left for x squared is 1. D must equal 1. Knowing that, I'm going to make this go even nicer. ax plus b plus 1x squared minus 4x plus 6. And then I can see that negative 3x must be equal to ax minus 4x. So negative 3 equals a minus 4. That means a is equal to 1. And then I have b plus 6 must equal 7. B must equal 1 as well. Woohoo! So sometimes finding the fraction decomposition can go really quickly. My integrand is now changed to ax plus b would be x plus 1 divided by that denominator, and then plus sign. Cx plus d turns into just the number 1 over its denominator. And here we are. So the reason we prefer not to have quadratic factors if we can factor it further is because now at this point, I could solve the entire integral through just trig substitution, but I could lessen the amount of trig integration that results from that trig substitution, which could potentially get rid of some really awful things if I figure out what can I take and let u substitution get through it. Now, regardless of which of these two I'm using, if I'm able to do a u substitution, that u is going to be x squared minus 4x plus 6. The derivative is 2x minus 4. Now, as I look at my first numerator, if I flat out split the x and the 1, the u substitution isn't going to work. When I factor out this 2, I can see that if that numerator had been x minus 2, a u substitution would be usable. But it's not x minus 2, it's x plus 1. However, I can rewrite it as x minus 2 plus 3. And then I can split the numerator at that addition sign. That will save me some pain when it comes to the trig integral that the trig sub leads to. So I'm going to now rewrite that I am solving the integral of x minus 2 over that business squared plus 3 over that business squared. And then when I look at this one, do you see that because I don't have an x term, u substitution can't even do anything. It can't touch it. It's these x terms that we want to set aside for u substitution that will allow the trig integrals that we eventually get to be fewer trig integrals. And also this might create some worse trig integrals that we don't really want to do. But if you want to go straight in and do the whole thing with trig sub, you can do it if it works out. All right. Now, oh, I forgot to write that part down. Plus the integral of 1 over x squared minus 4x plus 6. And I could split this up into 3 integrals, but that's what I'm working with. Let's start with, I've got a u sub. Let's take care of integral number 1. With the u sub, I want to see that x minus 2 dx is replaced with a 1/2 du. And the only thing left is to put a u squared in the denominator. When I integrate u squared, I'm actually integrating u to the negative 2. And so ultimately I am getting negative 1 over 2 u, where the u was x squared minus 4x plus 6. And then I continue. I'm going to put a big giant plus sign, start a, hey, final answer. And now it's time for trig substitution. Both of these next two integrals are going to use the same exact trig substitution. And I'm going to do this to kind of focus a little bit better. There we go. Okay. Oh dear, I don't have a sum or difference of squares. What am I going to do? We're going to complete the square. Woo, woo! Yeah. So let's do it. Do you remember how to go about completing the square? I'm going to give you a moment to try it. Mm-hmm. When I'm completing the square, I need to have a leading coefficient of 1. And then I need to find just the right number that will add to that x squared minus 4x duo to create a binomial square. But I must compensate and not only add that number, but subtract it. Are some of you seeing that completing the square actually isn't that much work? Good. So my b term is negative 4, divide by 2, and square that number. And completing the square is done. let's see, I'm going to highlight who that is. And then I want to look at what is the function that is being squared and what is the number that is being squared. And that is the same as what I have highlighted in the other problems. If I'm going to make a right triangle and have one of the sides of the right triangle be this under a square root, then I'm only going to add squares if I'm adding my leg squareds. So those are my two legs of a right triangle. And then my options are, I can use tangent and cotangent. I would prefer tangent. Opposite over adjacent, and then Pythagorean theorem says leg squared plus leg squared equals hypotenuse squared. Alrighty. And this is why we choose to use tangent theta for our trig substitution. And we want to set it equal to the function that is being squared divided by the number that is being squared. And you may want to, as you're writing that out, multiply both sides by root 2. Or leave it as is, and in your mind, multiply by root 2 as you throw things together. So that's my u quote part of this trig substitution. I need the du. So I take the derivative, and I'm going to do it from this point of view. So constant multiple, derivative tangent. Everybody? Woo! Yeah! Secant squared theta d theta. And then on the right, derivative of x minus 2 dx. Then I'm going to make my life a little bit faster if I can figure out what this is equal to. So when I go over to my triangle, I take that result of quadratic formula side and the side with just the constant. That's going to be hypotenuse over adjacent. And that means it's the reciprocal of cosine. And who is cosine's reciprocal? Secant. I'm going to multiply actually, I don't have a square root, so I'm going to first just square both sides. And then I'm going to multiply the 2 over. And now I have that highlighted portion is 2 times secant squared theta. And now I'm ready for my trig substitution. I have the integral of 3 over highlight squared dx plus the integral of 1 over highlight times dx. The highlight is equal to 2 secant squared theta. And then I have to substitute into the dx. And the dx is equal to root 2 secant squared theta d theta. Whew, we're getting there. We're getting there. For the second of the three integrals, I end up with a constant of 3 root 2 over 2 squared. And then I have a secant squared over secant to the fourth. And who is secant's reciprocal? We're going to come back to that trig integral. Let's look at what the third of the three integrals is when I simplify it. I get a root 2 over 2. And then my secant squareds cancel each other just completely out of existence, and that is ready for integration. Oh, yeah. Ooh, 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 ooh. I only have to deal with that cosine squared theta d theta and a little bit of converting back. It's not too bad, right? Right? Yeah. I see a head shake. Okay, so what do we do if we need to integrate cosine squared? Do you remember? Mm-hmm. And before I forget that there's an addition over here, I have root 2 over 2 times theta when I integrate. I'm going to combine my constants. And then the integral of 1 with respect to theta is theta. And then what is the integral of cosine 2 theta as you do a u substitution? You want to be good at u substitution. If u is 2 theta, and the derivative of that is going to give me 2, that means I have an extra 1/2. And then the integral of cosine is sine. Put that u back in, and it is a positive sign when I integrate. And then I have my plus root 2 over 2 theta over there. Now, I'm almost done, kinda. Sorry for the evil cackle. But it's kind of funny, isn't it? Just when you think you're almost done, then it's like, well, wait a minute. Okay, so theta, sure, I can convert back. For theta, converting back means I go back to my original substitution way over somewhere and do inverse secant of that business. Oh my gosh, you're right. I didn't go back far enough because that was ugly. This is prettier. Inverse tangent of x minus 2 over root 2. Now I've got this. It's not ready for going back to the original x variable. Do you remember what we need to bring in? Another trig identity. Sine 2 theta is 2 times sine theta cosine theta. 1/2 times 2. And all I have here is plus sine theta times cosine theta. Back to the triangle. Sine theta is opposite over hypotenuse. Cosine theta is going to be the adjacent over hypotenuse. Actually, give it, Taya, raise your hand. And then I'm going to be done. So that was x minus 2. And I'm just going to bring them together. And root 2 over. And then the hypotenuse is the square root of that quadratic we started with way over here. But it is multiplied twice, so just it, which was x squared. See you later. X squared, and now I forgot, minus 4x plus 6. And hold on, plus C. Woo! Woo! Yeah. Yes.
Why are we using the original denominator and not the hypotenuse of the triangle? Oh.
Yeah. Yeah, because I didn't want to have, I felt like it was easier to write it in the quadratic form than the, but you know, you can write it in either form. And if you're curious, you can see, you can look at, wait a minute, am I missing? I'm missing part. Yeah, I forgot this part, which was why I started. That's funny, isn't it? I'm going to lasso it. Whee! Whee! There we go. Now we've got the answer. Who had fun? Okay, now on. This could have been done completely by trig substitution. And it may be that this, instead of being an answer to a U sub, you went through a trig substitution, which took you to a trig integral, which you then solved and converted back. That's why we do U substitution as much as we can. Okay, now, tomorrow, oh, let me stop the recording.